Time complexity deep dive, comparing algorithms with big O notation. Hello, future computer scientists. Welcome back to our channel where we dive into the fascinating world of algorithms and programming. In today's episode, we'll explore the time complexity of different algorithms like linear search, binary search, bubble sort, and insertion sort in detail. We'll also dive deeper into big O notation and space complexity. So let's get started. Part 1. Linear search and binary search. Examples first, let's take a look at the linear search and binary search algorithms and understand their time complexities through pseudocode examples. Linear search time complexity. O of n. Observe the algorithm here. This algorithm searches for an item in a list by iterating through the elements one by one, starting from the beginning. In the worst case scenario, the item is the last element in the list, requiring n comparisons, where nn is the size of the list. Binary search time complexity, O of log n. Observe the algorithm here showing the binary search function. This algorithm searches for an item in a sorted list by repeatedly dividing the search interval in half. With each iteration, the algorithm eliminates half of the remaining elements. The worst case scenario involves log 2 of n comparisons, making it faster than linear search for large data sets. Part 2. Bubble sort and insertion sort examples. Now let's examine the time complexities of bubble sort and insertion sort algorithms using pseudocode examples. Bubble sort, time complexity, O of n square. Now check this bubble sort pseudocode function. In the worst case, bubble sort requires n1 comparisons for each of the n elements in the list, totaling n minus 1 into n over 2 comparisons. For very large n, we can approximate this as n square, making bubble sort a quadratic time complexity algorithm. Insertion sort time complexity O of n square. For better understanding, observe this insertion sort function pseudocode. Similarly, insertion sort involves nested iterations over the dataset. In the worst case, each element requires comparisons with all the preceding elements, leading to n minus 1 into n over 2 comparisons. Like bubble sort, the time complexity of insertion sort is also O of n square. Part 3. Big O notation and order of growth. Expanded explanation. Let's dive deeper into big O notation and see how it helps us classify algorithms based on their running time or space requirements as a function of input size. We'll focus on the worst case scenario when comparing algorithms to better understand their performance for very large data sets. Here's a more detailed breakdown of the algorithms we discussed and their order of growth. This table provides a quick reference for understanding the different types of big O notations, their time complexity, example algorithms, and descriptions. O of 1, constant time complexity. The algorithm's complexity does not change regardless of the dataset size. For example, retrieving the first item in a list takes the same amount of time, whether the list has 10, 100, or 1000 items. This type of algorithm is very efficient because it doesn't matter how big the dataset is, the operation time remains constant. O of n linear time complexity. The algorithm's complexity grows linearly with the dataset size. Let's take linear search as an example. If the list doubles in size, the search time will approximately double as well. So, if a linear search takes 1 second to search through a list of 1000 items, it would take approximately 2 seconds to search through a list of 2000 items. Similarly, bubble sort on an already sorted list would also take linear time, as it would only need to perform one pass over the list. O of log and logarithmic time complexity. The algorithm's complexity grows logarithmically with the dataset size. In these cases, each comparison reduces the dataset significantly. Let's consider binary search. If the list size doubles, the search time increases only by one additional comparison. So, if a binary search takes 10 comparisons to search through a list of 1024 items, it would take only 11 comparisons to search through a list of 2048 items. This type of algorithm is very efficient for large data sets. O of n square, quadratic time complexity. The algorithm's complexity grows quadratically with the dataset size, often involving nested iterations. Let's take bubble sort as an example. If the list size doubles, the sorting time will approximately quadruple. Part 4. Space Complexity. Expanded Explanation. Space complexity is an essential aspect of algorithm efficiency as it refers to the memory required for a growing number of values and in the dataset. Let's dive deeper into space complexity and see how it affects the algorithms we discussed. Here's a summary table of the space complexity for the algorithms discussed just now. This table provides a quick reference for understanding the space complexity of the discussed algorithms, helping you make informed decisions when choosing an algorithm based on memory requirements. Linear search, binary search, O of n. These algorithms only take the space required for the dataset, as they don't require extra memory for processing larger lists. For example, if we have a dataset of 1,000 items, these algorithms would need memory to store those 1,000 items. If the dataset grows to 2,000 items, the memory requirement would also double. Despite the memory growth, these algorithms are still relatively efficient when it comes to space complexity, as they don't use additional memory during processing. Bubble sort, insertion sort. O of 1. These sorting algorithms have a constant space complexity, meaning they do not require extra memory for sorting larger lists. They perform the sorting operations in place, using the same memory that holds the original dataset. To illustrate, let's say we have a list of 100 items to sort. Bubble sort and insertion sort would not need any extra memory beyond what is needed to store the 100 items, even if the list size grows. This is because they only use a few additional variables, like temporary variables for swapping, during the sorting process, which remains constant regardless of the dataset size. As a level student, you may have encountered situations where your computer or smartphone slows down or runs out of memory when handling large files or running complex applications. Understanding space complexity can help you appreciate the importance of choosing efficient algorithms that consume less memory, especially when dealing with large data sets. And there you have it. We've explored the time complexities of linear search, binary search, bubble sort, and insertion sort in detail using pseudocode examples. We also dove deeper into big O notation and space complexity. Remember, when choosing an algorithm, it's essential to consider both time and space complexity, as different scenarios might require different trade-offs. Thank you for joining us in this exciting exploration of algorithm efficiency. Don't forget to like, share, and subscribe for more insightful computer science content. Until next time, keep learning and happy coding. Bye.